Now we will start with the very first electrical machine, which is the transformer. Okay, so what is the basic working principle of transformer? It is the Faraday's law. Okay, so what does this state mathematically? E induced is equal to N times d phi by dt. So that means if you consider a loop like this, a conducting loop where presently there is no current flowing, let us say. Okay, now there is some magnetic field, time varying magnetic field, that is going into the plane. Okay, so we will mark it as B bar of T. Now this time varying magnetic field, it is going to induce a voltage in this conducting loop. Okay, and because of which a current will flow in this loop. Now say this conducting loop, there are n number of turns. Okay, then that much amount of voltage will be induced, n times d phi by dt. Okay, so similarly the current will increase. Now the next question is, what is the direction of this current? Okay, so that is given by Lenz's law. So if you remember, Lenz's law is nothing but the Faraday's law only, except that you add a negative sign. So E induced is equal to minus N d phi by dt. So what does this negative sign indicate? It indicates that the induced EMF will be in such a way that it will oppose the change in the flux. Okay, so we'll consider the magnetic core. Okay, now on this magnetic core, for a transformer there are two windings, but we will start with the first winding. So this is the first winding to which we are giving a AC source, right? So now the current is alternating current, remember that. So when the current is alternating, the flux that is produced by this winding, it is also going to be alternating. That means we are getting a time varying magnetic field. So now when the current is flowing in this direction, that means in the positive half cycle, right? So when the current is flowing in this direction, what will be the direction of the flux, right? The direction of flux is going to be in the clockwise direction. So we already discussed how to get this direction, right? You have to use the right hand rule. Wind your fingers, curl your fingers in the direction of this current here, and the direction of your thumb will give you the direction of flux. So this is flux. Now what we will do, we will consider the alternating current, different portions of the alternating current. Okay, so this is current I. Now in the first quarter of the cycle, the current is increasing and it is positive, right? Now what is happening when the current is increasing, the flux that is produced because of it is also increasing, phi is increasing. So that means phi is changing, increasing with respect to time. So the induced EMF should be such that it should oppose the change in flux. Okay, so this flux is going to cause an induced EMF across this winding. So what is that induced EMF? It is going to be like this. So we will take it as 1, so that this is the first winding. Okay, so we have an induced EMF here. So why did we take this polarity? So if you consider the entire winding as some sort of a voltage source, okay, so if this is a source, then the current will be driven in this direction, right? If this is the positive polarity, it will drive current in this direction. So if current is driving in this direction, then it is opposing this already existing current. So that means it is opposing the flux. Okay, so that is the induced EMF. So when you give an AC, an alternating voltage, to a winding, an induced EMF is produced. Okay, now this induced EMF, it will limit the amount of current that is flowing in the winding. Okay, so that is one of the reasons why DC input is never given to a transformer. Okay, so when you give a DC, there is no transformer action taking place because there is no time varying field, but it is dangerous to the transformer itself because in the absence of no induced EMF, a large amount of current will flow, right? And because of which the windings will be damaged. Okay, so DC should never be given to a transformer. So DC input should never be given to transformer as it results in large amount of current to flow. This will damage the windings. And why large amount of current will flow? Because there is no opposing EMF. Okay. So you can write AC input will result in an opposing induced EMF, which will help limit the current in winding. Okay. So this is the first part. We are only discussing about one winding here. So we will discuss about the second winding. So the second winding we will take here. Okay. Now here this is open circuit initially. Later on we will discuss about connecting the load. Now initially this is open circuit. Now what is happening in this quarter cycle? So I will mark this as pi by 2, pi, 3 pi by 2 and 2 pi, right. So from 0 to pi by 2, what is going to happen here? The current is increasing, the flux is also increasing. Now in this coil, the voltage should be induced in such a way that is opposing the change in flux. Since flux is increasing, induced EMF should be such that it should oppose that increasing flux. So if the current, if it is assumed to be flowing in this direction, okay, then what will happen? This current will be in this direction. Now if you apply the right hand rule, you can see that the flux due to this direction of current will be in the upward direction, okay, that is opposing this flux. Okay. So here anyways this is open circuit, so the current actually will not flow, but from here we can write the polarity of induced EMF. What will be the polarity of induced EMF so that it can drive a current in this direction? That is the question. Okay. So it will be like this. This is E induced 2. Okay. So remember this coil here, it will work as a source. So the positive polarity will be where the current is coming out. If it is a passive element, that is different. But here this winding is like it's now acting like a source, right? So this is how the voltage is induced in this period 0 to pi by 2. Now from pi by 2 to pi, what is happening? The flux is decreasing. So now the induced EMF, they should be in such a way that this decrease in flux is opposed. So the polarity will now be reversed. Okay, this will become negative and this will become positive polarity. Similarly in this case. Okay, so as long as flux is decreasing, the polarity will remain the same. Now once again when flux starts increasing, okay, then again this polarity will be got back. So you can see one more important point, that the induced EMF will be 90 degrees out of phase with the alternating flux. So this is the basic working principle of the transformer. So this is basically called as the transformer action, right? There is no electrical contact between this winding and this winding, but a current in this, it is going to induce a voltage in this, and if it is a closed circuit, it is forming a closed circuit, then a current will flow in the secondary winding. Now in this Lenz's law, you can see this negative sign, whatever is there, often this is ignored. Okay, why? Because if we choose the proper polarity, we don't have to worry about the negative sign. Okay, next we will see what is the expression for the induced voltage in transformer. So if the flux we are going to take as a sinusoidal function, let flux phi is equal to phi m sin omega t. Then what is induced EMF? This is going to be n d phi by dt. So this you are going to get as n omega phi m cos omega t. And further in terms of frequency, this is the angular frequency, right, radians per second. So we often want in terms of hertz. So omega is 2 pi f. So 2 pi F into N into phi m cos omega t is the final expression for the induced EMF. Okay. Now we want the RMS value. The peak value will be what? This will be the peak value, E maximum. Now if we want E RMS, then it is going to be peak value divided by root 2. So this is going to be root 2 pi f n phi m. So this is one important expression. It gives an idea as to what factors the induced EMF will depend on. Now we will discuss the characteristics of ideal transformer. So ideal means they don't exist practically, right? So a certain assumptions are made here. So what is the very first assumption? That the windings have zero resistance. They don't have any resistance. Okay, so this is one assumption. When there is no resistance, it means that there is no power loss, ohmic power loss, I square R losses, and there is also no voltage drop in the transformer. Okay, so but you will see in the practical transformer this is not going to be the case. And the next assumption is there is no leakage flux. Whatever flux is there, it is assumed to pass entirely through the magnetic core. All of the magnetic flux is assumed to flow within the magnetic core. And third point is the core is assumed to have infinite permeability. So that means if you draw the magnetization curve, here you have B and here you have H. You can also write phi and MMF. Now mu is nothing but the slope. Now if slope is infinity, then what will be the curve? The curve is going to be a straight line. Okay, and only till saturation. Again at saturation it is going to become constant. The magnetic field density is going to become constant. Okay, so this will ensure that there is no magnetizing current. So we will learn about magnetizing current, but for now just know that if mu is infinity, the permeability is infinity, then no magnetizing current will flow. And finally the core losses are considered to be 0. So basically there is no ohmic losses, there is no core losses. So we have a lossless machine here. That is the ideal transformer. Now the most important point for the transformer, for an ideal transformer we will discuss first the voltage and current ratio. So what will be the induced voltage of the primary winding? We can draw the winding here. This is the core, let us say, and this is the primary winding, this is the secondary winding. On the primary side we apply the voltage source, right, and here the induced EMF we will take as E1, and on the other side secondary winding we will take the induced EMF as E2. Now this voltage source here, this voltage we will take as E1, V1. Okay, so as you can see, for an ideal transformer V1 is nothing but it is equal to E1. Okay, and here also the terminal voltage we will take as V2. Okay, so why we are taking this differently even though they are equal, you will understand when we are discussing the practical transformer. Okay, so now what is the expression for the induced EMF? This is equal to, if you take the number of turns here as N1 and this number of turns we will take as N2. So this is going to be N1 d phi by dt, and similarly the secondary winding induced EMF, this is going to be N2 times d phi by dt. So what does this mean? E1 by E2 is equal to N1 by N2. So this is one of the most important expressions for the transformer. Okay, and further for an ideal transformer, V1 is equal to E1 and V2 is equal to E2, right? So V1 by V2 is equal to E1 by E2 is equal to N1 by N2. But remember, this is only for the ideal transformer. This will be applicable for practical transformer as well. Okay. And often another way of representing this ratios is, instead of 1 and 2 subscripts, we can write P and S. Okay. So subscript P means it is relating to the primary winding. In fact, this is more convenient. Okay. And S is the secondary winding. So if I am using an expression called Vp, then this is going to be the voltage at the primary side. Okay. So don't get confused, we will use these notations interchangeably. Next we will discuss the current ratios. Okay. So when will the current flow? When you are connecting a resistor, say, on the secondary side, then the current can now flow on the secondary side. Now when current flows here, then there is going to be an MMF here as well. Now one thing that you have to remember for the case of an ideal transformer, okay, I am talking about the ideal transformer here, only when the current flows in the secondary circuit, then secondary winding, then only current will flow in the primary winding as well. If the secondary winding is open circuited, then the primary winding will not draw any current. So you can write primary current does not flow if secondary winding is open circuited. That means at no load. Okay. So remember, this is for ideal transformer. For practical transformer, there is going to be a no load current, about which we will discuss. Now coming back to the current ratio. So let us say the current that is flowing in the secondary winding, it is I2. Okay. And if I2 flows, then some current I1 is going to flow here. Okay. Now what is the net MMF that is present in the circuit? One MMF is because of this current I1, N1, and the second MMF is because of N2 into I2. Okay. Now these two MMFs, they will be opposing in nature, right? So if you want to write the total MMF, the net MMF, this is going to be N1 I1 minus N2 I2. Okay. But from the magnetic circuits, we also know that the net MMF is equal to the flux into reluctance. Okay. Now what is the reluctance here? This is given by the mean path, flux path divided by mu into A. Okay. But for an ideal transformer, mu is infinite. Okay. So for an ideal transformer, the reluctance is going to be 0. So MMF is going to be 0. Flux will not be 0. Okay. Only the reluctance is 0. So here you are going to get MMF net is equal to 0. This means that N1 I1 minus N2 I2 is equal to 0, or otherwise N1 is equal to N2, right. So from here you will get the current ratios. I1 by I2 is equal to N2 by N1. Okay. So now if you combine the voltage as well as the current ratios, what will you get? E1 by E2 is equal to N1 by N2, but the currents will be reciprocal, right? I2 by I1. So this is the voltage and current ratios of ideal transformer. It applies for a practical transformer as well, if you consider the induced EMFs here. Okay.